Welcome to Textile Update, the podcast where we can share our passion for textiles, fibers, and yarns. This is Gwendolyn Hustvedt. This is the first episode that focuses on cellulose fibers, and today we'll talk about the properties of naturally occurring cellulose fibers, the good, the bad, and the ugly. To be honest with you, I just don't feel the same way about cellulose-based fibers as I do about protein fibers. It could be because I, as one of my artistic pursuits, engage in silk painting, which is on a protein fiber, because I love knitting, which is, let's be honest, just really well done with wool. Honestly, I don't enjoy the hand of knitting with cotton. It has sort of a crunch to it that's just unyielding. Although I may really love the protein fibers because I actually love an underdog. Cellulose fibers are a hugely important part of the global apparel textile industry. The government of the United States and taxpayers have funded billions of dollars in research on how to make cotton better. Cotton is a hugely important fiber in the development of the civilization that we now enjoy, modern Western civilization. It plays a very important part in the history of the United States of America. So I think that some of my bias against cellulose fibers has to do with the fact that they already get so much play, right? They already have whole websites devoted to them, and at any rate, this very first introductory conversation is just to focus on the good properties, and there are plenty of good properties. But before we get into the properties, I need to introduce the idea that unlike protein-based fibers, where we really just have two major things to examine. Did it come from the hair of a mammal, or was it extruded by an insect, right? That's the big question. With cellulose fibers, we actually can think about what part of a plant the fibers came from, because the parts of the plants the fibers came from influences the properties that they have to a certain extent. And thinking about why the plant evolved to have a fiber in that location can tell us a little bit about what the fiber might be good at. So let me set this up. There's three main places that a fiber can come from in a plant. It can come from what are called seed hairs, right? So something around the seed. It can come from the stem. Fibers from the stem have been traditionally called bast fibers, B-A-S-T. Yeah, like the Egyptian cat goddess, bast fibers. And then, of course, we can also get fibers from leaves. So if you think about, on a plant, right, it has a stem. It has leaves that collect sunlight and do photosynthesis. And then we have the seeds, which are the sexual reproductive organs of the plant, and the result of the reproduction, because the seed is the embryonic future plant. But the only part that's missing from this story are the roots, and in some cases the roots are very similar to the stem, right? As they're fibrous that help the plant anchor in the ground. But of course, the roots, like the stem, also serve as this conduit purpose, channeling moisture from the ground up into the plant. So we can see that the purpose of the stem is really something to do with sturdiness and structure. The purpose of leaves are also about sturdiness and structure, right? But they may be they're more about kind of being the major girders in an anchoring in a net of cells that conduct photosynthesis, and the purpose of the plant is to nurture and protect the embryonic seed. So it doesn't really surprise me that the fibers that come from seeds are some of the most absorbent fibers. It seems like something that a little embryonic plant would need, right? Plenty of moisture. In other cases, fibers like milkweed are very, very light and downy and have a lot of they're very fluffy because they're there to transport the seed across a distance, and so they actually help the seed float. A fiber like kapok, which is comes from the seed hairs of the kapok plant. Kapok is used in life jackets. It floats. Coir, which is on the outside of cotton, isn't necessarily absorbent, but it really protects that coconut from the degradation of strong sunlight and the salt water in the ocean as the coconut is floating from island to island, right, spreading its seed. Whereas the bast fibers, linen, comes from the hemp plant. We can also make linen, it comes from the flax plant. We can also make linen from hemp. And jute, ramie, kenaf, these are all fibers that we extract from the stems of plants, and they're all very sturdy and durable and not known for their softness or absorbency, right? More known for their structure. And then piña, abaca, sisal, that comes from leaves, are all very stiff. Right? They end up kind of having an issue with stiffness over the course of their life. They don't necessarily ever settle into the softness that we might see even from a bast fiber that, like linen, over time will become soft as it's worn down. I'm going to take the chance that you're open to talking at least about one polymer in more depth than we might have been able to talk about. I didn't start with the protein fibers because the amino acids are also varied and relatively complex compared with glucose. So let me describe the mer, the glucose mer, which is what forms up the cellulose polymer. It is a ring of five, 5 carbon molecules. There is an oxygen, right? So it goes oxygen, carbon, 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 oxygen. And one of the carbons right next to the oxygen is bonded with an oxygen that's outside the ring. And then another 2 carbons away from that oxygen is also bonded with an oxygen that's outside the ring. And then each of the different carbons will have hydrogens or hydroxy groups or methyl groups. And the fact that each of these carbons has an additional site, above or below it that is open to doing chemistry, right? That hydroxy group or that hydrogen, those are all open to doing chemistry. That is part of what makes the cellulose polymer so absorbent and so easy to dye, DYE, dye. But the fact that the oxygen is in between each of the carbon rings is something that means that the bond that connects each of the mers in this polymer is actually a bit stiff and unflexible. So think about an image you might have seen of a water molecule. Big, juicy oxygen with 2 little hydrogens that are perched up top, kind of like a cartoon, a Pokemon character, right? With 2 little stumpy arms up top. And those 2 hydrogens up at the top are up at the top for specific chemistry reasons. So it's not like they are exactly opposite of each other. They are somewhat next to each other. And that means that the bond that the oxygen forms is either kind of in a V shape pointing upwards, or if it flips over and forms the bond upside down, a V shape pointing downward. It's not a straight line across. And so that V shape pulls the 2 cellulose or the glucose molecules close to each other, right? And this oxygen can form a very nice strong bond, but this does mean that there's a little bit less flexibility in the relationship of the mers to each other in the polymer. Because of these kind of V-shaped bonds. So these strong inflexible bonds in the polymer mean that the durability of the cellulose fiber is high, right? Not quite as high as it could be if the bonds were even tighter and even stronger. Because they're inflexible, we have less elongation, less elasticity, and less resiliency, right? It's kind of like a bent arm, that V-shaped bond, that the only way we actually change it is by breaking the arm, and then we've damaged the polymer. Because the cellulose in nature is created by the enzymes that produce the polymers, they have a very high degree of polymerization, which I sometimes just call DP, just to, have a cool lingo, right? But the degree of polymerization means that there can be up to 10,000 glucose molecules in an average cellulose polymer inside of a naturally occurring fiber. And when we get to manufactured cellulose fibers, we'll understand why 10,000 is so great. The cellulose molecule is capable of crystallinity and can be laid down in an oriented way, so parallel to the axis of the fiber. But again, this isn't something that would just happen if we threw glucose in a beaker and stirred it around and hoped it turned into cellulose polymers. This is something that happens because the plant is building the polymer in an organized way. So compared with protein fibers that have shorter chains, so lower degree of polymerization, and are fairly amorphous and don't form crystals because of the variety of amino acids, cellulose fibers are stronger. They have higher tenacity. But when we compare it with synthetic fibers that are even more oriented or even more potentially crystalline and have an endless degree of polymerization, they are going to be somewhat less tenacious, right? So polyester is going to beat an arm wrestling fight with cotton, but cotton will wipe the floor, and not just because it's absorbent, wipe the floor with rayon because rayon is so disorganized and the polymers are so short. So as I just mentioned, the tenacity, pretty good, moderately strong. And one of the cool things about cotton is that the wet strength increases when we get it wet, right? So it goes up about 10 to 30%. This is compared to protein fibers, which, as you might remember, I warned you, might need to be dry cleaned, or at the very least treated as gently as you treat your own hair because the wet strength was less, right? But with cotton, throw it in a washing machine and it actually is even better. So that's part of the reason why we ended up, making most of our apparel out of cellulose fibers. The absorbency is good. The moisture regain on protein fibers, 11 to 18%. The moisture regain on cellulose fibers, 7 to 12%. So still pretty good compared with synthetics that might have a moisture regain of 0. So the moisture regain means that you can dye it because DYE, dye it, because it will absorb water, which is what carries the dye. On the downside, it means that it does dry slowly, right? So if you get wet in cellulose fibers, you won't be dry the next minute. Launder something cellulose in the sink of your hotel, for example, and it's maybe a bit of a crapshoot if you're going to be wearing damp something the next day. Heat resistance, great, right? You remember that protein fibers, we were a little worried about that. We couldn't iron them with a really hot iron, but with cellulose, good thing because it actually has poor resiliency, wrinkles badly, so we got to get out the iron. That's a bad. I'll get to bads in a minute. I'm getting to bads right now. Cellulose fibers burn, and I didn't even get to this with protein fibers because it just seemed like a a little soon to be introducing this idea that we just might light textiles on fire, but I think you can understand. Cellulose fibers are made out of, like what trees and paper are made out of. Yeah, it burns. So flame resistance is poor. And actually, we use the difference in flame resistance between protein fibers and cellulose fibers for a quick ID, right? So if you're not sure, potentially the bridal shop is selling you a highly priced wedding gown that's not actually made from silk, right? One way that you can tell if it's made from rayon, which rayon is the fiber that is most often mislabeled as silk. Rayon is the reason we have laws against mislabeling textiles. Even recently we've had to deal with this question. You can just ask for a swatch of the fabric that the garment is made out of. Step outside, light that puppy on fire. If it burns quickly, right, smells like paper while it's burning, and leaves a white ash with a bit of an afterglow, then yeah, you just lit cellulose on fire. If it is sluggish to burn, right, in the flame, or it burns in the flame, and when you pull it out of the flame, it sputters and self-extinguishes, and when it cools, it leaves a black ash, right, with a crushable bead, so it's sort of a little black lump that when you squeeze it with your finger, just softly degrades into black ash on your finger as opposed to gray ash from the cellulose. Then you know that likely you're being sold a silk gown as opposed to a rayon gown. Let's see, what else is great about cellulose? It resists bleach and alkalis, which is great because many laundry additives, detergents, and as I mentioned, bleach are more on the alkali side. It does not resist acids very well, right? So that's something you discover if you're wearing jeans in the chemistry lab and you drop a little bit of sulfuric acid on your jean. All right, it'll just eat right through the cellulose, and then you're freaking out like, is the acid gonna burn my leg? All right, rinse it, and you'll just be left with a hole in your jeans. UV resistance is also poor, like protein fibers. In the case of protein fibers, that just makes the fibers weak. In the case of cellulose fibers, they actually begin to yellow with age. You've seen like really old stacks of newspapers, maybe, right? And they actually, the cellulose fibers will turn yellow with age. Protein fibers are edible, right? Well, cellulose fibers are edible too, only to different creatures, right? Protein fibers, we worry about carpet beetles and clothes moths. With cellulose, we worry about silverfish, which will eat the cellulose. We also need to think about mold and mildew, these fungal organisms live on trees and leaves and cellulose in nature, so it only makes sense that they would be attracted to cellulose in the textiles. So these are all issues more with humidity, which make the cellulose a little more juicy and livable. So there we have it. Just a basic summary of kind of what's great about cellulose fibers, naturally occurring cellulose fibers, right? Launderability, big star when compared with protein fibers. The fact that it's highly flammable, somewhat problematic for some specific end uses. And that is our introduction to cellulose. In the next series, I'm going to talk very specifically about cotton.